Assalamu alaikum. Welcome to lecture 23 of data mining. So we are nearing the end of this semester. We have 28 lectures left and we have an eat break between that as well. So, uh, so we have only a few topics left to cover. Uh, the main topic that we were discussing before so the topic that we were discussing in the previous lecture was outlier detection. So this is one of the main topics that we wanted to cover in this course. So after this topic, there will be some additional topics which are not primarily given in your main textbook. They will be available from other textbooks. So we decide those topics later on for the remaining 3 lectures. We are also planning a guest lecture as well, maybe one or two. So someone from the industry who might come in and tell you about his or her experiences in the industry. So the remaining 3, 4 lectures would be covered on these small topics and a guest lecture. Mm. Mhm. All right. So we'll continue with our discussion on outlier and anomaly detection today. So we had started this discussion last time, and we noted that there are different types of outliers. So outliers could be global, they could be contextual, they could be collective. And then we also mentioned that the algorithms that are used for outlier detection can be categorized in different ways. One way is based on machine learning, whether it's supervised or unsupervised. The other way of categorizing such algorithms is based on the approach. Uh, so in this way, you have various categories. You can think of statistical approaches, you can think of proximity-based approaches. Then we have clustering-based approaches and also reconstruction-based approaches and so on. So we will continue this discussion today by talking about a proximity-based method which is called the local outlier factor. And then we'll discuss the reconstruction-based technique using an auto-encoder. And then we will discuss some additional topics like contextual and collective outliers as well. Are there any questions? So, so we were talking about outlier detection, and we had talked about what is known as distance-based outliers. So this was a global approach for finding outliers, and it required two parameters. One was the radius parameter, and the other was the pi, which is a fraction of objects that lie beyond this radius of an object. So, so these two parameters are again global parameters. They are defined for the entire data set. If an object uh, if an object whose neighborhood is that is defined by R has more than pi objects that lie outside this object, uh, would then be considered an outlier. So the one of the issues with this approach is that it uses global parameters. So the parameters are the same for the entire uh, question. So कोई question था किसी का? Uh, just right. Right. So I thought there was a question, but somehow वो आवाज नहीं आ रही. Okay. So these parameters R and pi are global. They are defined for the entire data set. But oftentimes data sets have varying densities. So densities may vary. So you may have a region with a high density within the same data set and another region with low density. And the problem with setting global parameter is that either you will set all the objects to be outliers or you will set all objects to be not outliers uh, if you choose one set of parameters for the entire data set. So we would like our parameters to be adaptive to the density in the neighborhood of a particular object. So, so this leads us to the another technique which is basically called the local outlier factor or LOF. So local outlier factor LOF. So this technique is based on relative density. It's a proximity based approach, but it's based on relative density. It doesn't have a global parameter that defines a notion of outlier over the entire data set. So this is, as I said, a proximity-based method. It's also unsupervised, and it uses the notion of relative density. So to explain this further, let me try to draw a figure. So let's say you have a sparse cluster, meaning that this is a big cluster with objects that are far away. And then you have some object here, let's say O1. So this object O1, of course, you can see it's far away from this sparse cluster. So it may not be an outlier with respect to this cluster, because this cluster itself has objects that are far away from each other. In other words, you can say that the density around this object O1 is kind of similar to the density of any other object that's within this cluster. But let's say if you consider another uh, object, another cluster, that says a smaller cluster but very dense. If you look at a point here, which is O2, this O2, if you look in terms of absolute distance, is very close to this cluster. It's very close to this cluster. But because since this cluster is very dense, this O2 can still be considered to be an outlier because its neighborhood is very dense and O2 is in a sparse region. So the point that I'm trying to highlight is we need to look at the neighborhood around a particular object and compare its density, meaning the density of that neighborhood, with the density of the neighbors of that object. So if an object lies in a sparse region while its neighbors lie in a dense region, then that object would be an outlier. Conversely, uh, on the other hand, if the object lies in a dense region and its neighbors also lie in a dense region, then it cannot be called a outlier. So we need to have a notion of relative density or define a notion of relative density and somehow quantify it. And then based on that quantification, we can then find out whether an object is an outlier or not. So previously, when we talked about distance-based clustering, we would have specified only global parameters like a radius r for the entire data set. So if you specified an r that was big, then all these smaller objects that I drew on the right would have been considered outliers. If we had specified that to be small, then you will have most of the objects on the left which are sparse, which are big, जो cluster बनाया था वो, that would be considered to be outliers. So, but since data sets may have regions of high and low density, we need to have a relative way of quantifying whether an object is a outlier or not. So is this point clear? Meaning that we are looking at the neighborhood of an object as well as the uh, neighbors of that object, and then deciding whether that object really is an outlier or not. So in words, so if an object O lies in a sparse region, while its neighbors have regions that are denser, then O is likely an outlier. ठीक है ना? So ये basic idea है इसका. So LOF, as I said, is a fairly popular technique. It has roots in density-based clustering, but it's primarily used for outlier detection. So requires a parameter called K, which is the K basically is the K nearest neighbor. So this is the input parameter, which is basically the K nearest neighbor. ठीक है? So you can set K, of course, K is equal to 1 would not give you much help. So usually K is greater than 1, 2, 3, 4, whatever, depending on your data set. So this parameter is required. So then we have a notion of the K distance or distance K, उसको भी कह सकते हैं, whatever you want to call it, K distance, ठीक है? So this is basically the distance to the kth nearest neighbor. ठीक है? So, so if I say K distance of an object O, so this is going to be a number, and this number is the distance to the kth nearest neighbor of this object. So let's say if K is 2, तो फर्स्ट नियरेस्ट नेबर होगा, सेकंड नियरेस्ट नेबर होगा, जो थर्ड नियरेस्ट नेबर होगा ना, उसका डिस्टेंस इस O से ये K डिस्टेंस होगा इस ऑब्जेक्ट का. ठीक है? So obviously if K is larger and you have the same data set, this K distance would increase. ठीक है? So you are looking at the kth neighbor of that object. If K is 1, then you're looking at the nearest neighbor and its distance from this object O. ठीक है? So this is the K distance. So this K distance actually dynamically defines the neighborhood of O. So we can define that neighborhood as N of O. So this is the neighbor of O. ठीक है? And this is defined, of course, by this parameter K. So it has all objects that are at most K distance away from O. ठीक है? So we use this Nk to denote this set of objects in the neighborhood of O. And we will use this notation N O, the bar of this set, to be the number of objects in this neighborhood. Okay. So now obviously you might be thinking कि ये जो number of objects in the object would be exactly k, तो ये k से ज़्यादा भी हो सकता है. क्यों हो सकता है? Because you might have multiple objects that have the same k distance from this O. So just to take a quick example, let's say 1D data set मैं लेता हूँ. 1D data set लेते हैं, let's say 5 है मेरे पास, 6 है, 6 है, 9 है, and let's say 10 है. ठीक है? सो इफ आई टेक ओ एज 6, ठीक है, द फर्स्ट ऑब्जेक्ट है, और के लेट्स से मैं कहता हूँ 2 है, ठीक है, तो k इज इक्वल टू 2, तो इसका n नेबरहुड में क्या होगा, व्हाट वुड बी एन ओ, so this would contain the object 5 obviously. The first nearest neighbor is 6 and the second nearest neighbor is also 6, ठीक है, so there are actually two objects uh, in this at this, and the k distance would be what, k distance of this object o, sorry, yeah, k distance of, so the k distance in this case would be actually 6 minus 5, which is just 1, ठीक है, and obviously the number of objects in this neighborhood is 3, ठीक है, so k, take k as the parameter, find the nearest neighbors, the k nearest neighbors, based on those k neighbors you get the k distance, ठीक है, k distance is distance to the kth nearest neighbor. So far so good. So now you can define the density around this object o, ठीक है, so in general density can be defined as n divided by you can say the average distance of the objects in the neighborhood of o, ठीक है, so if I want to uh, or you can simply take the sum as well, n is of course the number of objects divided by the average distance or some notion of area, ठीक है ना, डेंसिटी क्या होता है, नंबर ऑफ ऑब्जेक्ट्स डिवाइड बाय एरिया या वॉल्यूम या व्हाटएवर, तो सम नोशन ऑफ वॉल्यूम में आप एवरेज डिस्टेंस भी ले सकते हैं, डायमीटर भी ले सकते हैं, सो वी नीड टू फाइंड ए वे ऑफ क्वांटिफाइंग डेंसिटी, सो ऑफ कोर्स सम भी ले सकते हैं, तो वन वे ऑफ डूइंग दैट इज यू कैन से सिंपली से सम of all objects in the neighborhood of, so you have an object o prime which lies in the neighborhood of n, ठीक है, of their distance to the object o, ठीक है, o prime and o, ठीक है, dm is the actual distance. So usually we do a bit of smoothing on this, तो एटलीस्ट जो LOF टेक्निक है वो थोड़ी सी स्मूथिंग अप्लाई करता है, ये नहीं अप्रोच करता, इट डिफाइंस अनदर डिस्टेंस विच वी कॉल द रीचेबिलिटी डिस्टेंस, तो रीचेबिलिटी डिस्टेंस, ठीक है, so reachability distance of an object o, so reachability distance o प्राइम से o का reachability distance क्या है, ठीक है, so this is defined as the max of two things, from two things, uh, one is of course the k distance of the object o and then the actual distance between o prime and o, ठीक है, so what does this mean, so basically it's essentially meant for smoothing. So if an object O prime lies within the neighborhood of O, meaning that उसके neighborhood के अंदर O prime lie कर रहा है, तो हम उसका जो distance लेंगे वो reachability distance in this case would be the k distance of that neighborhood. And if that object lies outside the neighborhood, तो उसका actual distance लेंगे, max वो बनेगा. So if I want to draw this little bit, मतलब let's say ये आपका O है और इसका एक neighborhood है. If O prime is inside this, तो इसका हम full k distance लेंगे. K distance is the radius of this neighborhood. ऑन द अदर हैंड इफ ओ ये आपका है और ये नेबरहुड है, ओ प्राइम बाहर है, तो ये टोटल डिस्टेंस लेंगे फिर हम. सो फॉर ऑल ऑब्जेक्ट्स ओ प्राइम दैट आर विद इन द नेबरहुड, तो हम उसका फिक्स डिस्टेंस लेंगे, के डिस्टेंस, विच इज द रेडियस ऑफ दिस नेबरहुड सेंटर्ड एट ओ. जैसे ही ओ प्राइम बाहर निकलता है उस नेबरहुड से, तो फिर एक्चुअल डिस्टेंस लेंगे विच इज ग्रेटर देन के डिस्टेंस. ठीक है. सो ये आपके पास ओ है, ओ प्राइम इसके अंदर है, तो ये के डिस्टेंस इसका होगा. और लेट्स से ऑन द अदर हैंड इफ ओ प्राइम आपका इधर है, तो ये एक्चुअल डिस्टेंस होगा. सो इफ फॉर ऑल ऑब्जेक्ट्स विद इन द नेबरहुड ऑफ ओ, उसका reachability distance would be k distance. And when an object lies outside the neighborhood of O, it will be the actual distance. ठीक है. तो आर डी ऑफ ओ, basically O prime to O is given by this formula, and it's basically meant for smoothing. And then based on this, we now define the density, which we call the local reachability density. ठीक है. और एल आर डी ऑफ द ऑब्जेक्ट ओ. ठीक है. सो एल आर डी ऑफ ओ, so this is basically जैसे पहले लिखा तो वही चीज बनेगी, but now we are using reachability distance, n divided by we have to sum over all objects O prime in the neighborhood n. ठीक है. All objects, and then we use the reachability distance of to O, actually from O to O prime. ठीक है. So now this is defining the density of the region around point O, or is a way of defining the density around the point O. Exact density to nahi obviously, but it has the same concept. Number of objects divided by some notion of distance or area or volume. Okay. So essentially now we, from this definition, we define now our LOF, which is local outlier factor, which is a score, okay, as a ratio of the local reachability density of the neighborhood with respect to the local reachability density of the object in consideration. So, so LOF of an object O then is basically, so yeah, again, we will have a summation here. So we are summing for all objects O prime in the neighborhood of O. Remember this N is the neighborhood of O. Okay? All objects O prime in the neighborhood of O. So we take a ratio LRD of O prime divided by LRD of O. Okay? And then of course we normalize this. How many objects do we have in the neighborhood? We normalize with that. So normalization हम कह दें, बाहर लिख देता हूँ पहले 1 divided by n. ठीक है. So what is the summation over? Summation क्या है उसका? न्यूमरेटर में एल आर डी ऑफ ओ प्राइम है. And what is O prime is a point in the neighborhood of O. हम क्या देख रहे हैं, हम एक पॉइंट O देख रहे हैं और उसके नेबरहुड पे देख रहे हैं. अब उस O प्राइम जो O है, एक O प्राइम ले लेते हैं उसके नेबरहुड में. अब उस O प्राइम का अपना भी एक नेबरहुड है. ठीक है, उसका अपना भी एक नेबरहुड है, उससे भी एक डेंसिटी आएगी. So what this ratio is saying that if the density of points in the neighborhood of O is greater than the density of points at O, ठीक है, then this ratio will be greater than 1. What does this mean? जब density neighborhood की ज़्यादा है और इसकी कम है, ratio जो ज़्यादा है, greater than 1 है, तो इसका मतलब है ये outlier का chance इसका ज़्यादा है. So essentially LOF greater than 1 uh, implies that object O tends to be an outlier. So as I said, this is a score. तो जितना ज़्यादा स्कोर होगा उतना ज़्यादा चांस है O का आउटलायर होने का. And you can always rank all these scores and then you can cut off this rank to find which objects you want to consider to be an outlier or not. सारे objects के लिए LOF निकाल लें, उनको rank कर लें and so on. So obviously an LOF that is 1 or less than 1 would never be considered would never be considered as an outlier. For example, 1 कब होगा? जब रेशियो ऊपर एल आर डी ओ प्राइम और एल आर डी ओ दोनों सेम होंगे हर ओ प्राइम के. ठीक है, वो कब सेम होंगे? बिकॉज ओ प्राइम की डेंसिटी वही है, ओ की भी वही डेंसिटी. इसका मतलब दे आर इन ए होमोजेनियस रीजन. दैट होमोजेनियस रीजन में बी स्पार्स में बी डेंस, इट डजेंट मैटर. रेशियो लिए हमने, रिलेटिव लिए, तो दोनों की डेंसिटी सेम है, इसका मतलब इट्स नॉट एन आउटलायर. बट जैसे ही ये एल ओ एफ बढ़ता है या एल आर डी ऑफ ओ प्राइम ज़्यादा होता है एज कम्पेयर टू एल आर डी ऑफ ओ, then LOF would become greater than 1, and as it increases, that object O tends to become an outlier. ठीक है, so any questions on this? So LOF is a proximity based approach. It uses distances, but it then uses these distances to compute densities, uh, and it uses densities in a relative sense, considers the density of an object with the densities of the objects in its neighborhood, and from that it computes a score which we call the LOF, and that score would indicate the tendency of an object to be an outlier. If the score is larger, then it's more likely to be an outlier. ठीक है, so any questions on this? So इसमें जो reachability distance वाला है, that is only a normalization. You can or you can say a smoothing approach. But rest of the, I think, is quite intuitive. You are taking the ratio of the density in the neighborhood with respect to the density of the object itself. Okay. All right. So so this was LOF. Now let's talk about reconstruction based a reconstruction based technique. So reconstruction based outlier detection has become more popular in recent years and it's also popularly used in the industry. And this approach, the most common approach within this category, uses a neural network, which we call an auto-encoder. So the general idea, first of all, is like this. So we develop an encoder or a representation for the entire data set, right? So, so let's say you have a data set D, which consists of course, n objects. Okay? So you build a representation for this data set. And of course, while you're building a representation, there will be some losses and some errors and some smoothings, and all of these things will go into that representation. Then once you have the representation and you have an object which you want to determine whether it's an outlier or not, you basically get that object's representation using that model and compare it with the original date point. So let's say you have an object X. Let's say vector की मैं बात कर रहा हूँ. Object X as a vector, as a vector. ठीक है? So so X as a vector. ठीक है? So now whatever model you have developed, you will get a representation for that X prime, for example. ठीक है? So X prime is the represented form of this object X. You can say encoded form of this object X. Okay. And then what we do is we compare the actual object and the reconstructed or object from the model. If the difference is large, of course, you will have to quantify this difference. Usually it's a norm. Then you can say that this would be an outlier. Okay. So just let me repeat this again. So let's say, uh, so let me write it x minus x prime. If this is greater than some threshold, then x is an outlier. So what is x prime? X prime is a reconstructed uh, reconstructed representation of x using some model. ठीक है? And this model is developed over the entire data set. When you develop a model on the entire data set, it will learn the key features of that data set, and it will then try to regenerate those key features. So if an object deviates significantly from those key features, then it's likely to be an outlier. So that's the gist of the whole idea here. Okay? You train a model or you learn a model on the entire data set, that model would learn the the generalized behavior in that data. If you generate a representation from that model for an object and it deviates significantly from the actual object, it means that uh, the actual object was not part of the generalized model that you have learned from the data, or it was significantly different from the generalized model that you have learned from the data. So the model that is commonly used, as I said, is an auto-encoder. So this is actually a neural network, a feed-forward neural network. So auto-encoder is a feed-forward neural network. You have an input layer, okay? You have an hidden layer, and you have an output layer. And we'll, of course, if you draw a neural network, you can think of these as layers of units, but we'll write this as equations. That is much easier to understand. ठीक है? So इसकी जो processing क्या होती है? Uh, so input layer would take input, which is your vector x. So let's say vector x, जो आपका data object है, which is represented as vector, is of length, let's say n, has m features, so it has a length of m. ठीक है? So इसका मतलब input layer would have m units if you think of in terms of a neural network. So then we have the hidden layer. Hidden layer would typically have some units h, which is less than m. ठीक है? And then the output layer has again m units, meaning that we want to reconstruct this. ठीक है? So इसकी जो प्रोसेसिंग है वो इस तरह है. So जो हिडन लेयर की जो आउटपुट आएगी एज ए वेक्टर h, ठीक है? So this would be usually activation function, which is tangent hyperbolic function of a parameter. Let's say this is a whole matrix W. Uh, so there are actually two parameter matrices. So let me call this W1 into X. This is a matrix vector multiplication. So W1 is parametric matrix, ठीक है? तो दिस पैरामीटर मैट्रिक्स का साइज क्या है? इसका साइज बेसिकली आपके पास है h into m. Input is m, x is of size m, and then the hidden layer जो आपका small h जो आउटपुट होगा वो आपके पास कितने हैं? वो आपके पास बेसिकली कैपिटल h है. ठीक है? कैपिटल h इज एक्चुअली नंबर ऑफ हिडन नोड्स. इसको पता नहीं है अभी एक्शन. ठीक है, सही है. ठीक है. So now you can think of this h. इसको मैं h से कुछ और कर देता हूँ, e कर देता हूँ. यू कैन से द एनकोडेड वर्जन ऑफ दिस. सो इसको e वेक्टर कह देता हूँ. ठीक है. सो नाउ वी वी आर फेड द इनपुट टू द हिडन लेयर. अब इनपुट हिडन से फिर आउटपुट पे वापस लेके आएंगे. वो किस तरह होगा? सो आउटपुट लेयर पे आपके पास x प्राइम आएगा. ठीक है. ठीक है, ये भी टेंजेंट हाइपरबोलिक है. ठीक है. एंड देन वी हैव अनदर सेट ऑफ पैरामीटर w मल्टीप्लाइड बाय e. ठीक है. सो W2 का साइज क्या है? दिस इज अगेन अ पैरामीटर मैट्रिक्स. आउटपुट मेरे पास इसकी है m, और जो इसमें हम हिडन लेयर से जो यूनिट्स देख रहे हैं वो h है. ठीक है. e इज ऑफ साइज h. ठीक है. So the idea, we given a data set D, we train the network so that it can regenerate the input again. मतलब आपके पास एक इनपुट x था. So we'll get x prime. ठीक है. So we would like x to be as close as possible to x prime. So हमारा जो न्यूरल नेटवर्क का जो loss function, objective function, we would like to minimize this difference and we will train it over the entire data set. So the objective function है, so minimize the difference है, मैं जनरल फॉर्म में लिख रहा हूँ. यूजली जो स्क्वायर्ड लॉस फंक्शन यूज होता है बिटवीन x and x prime. What is x prime? Is the reconstructed form of x, or you can say the decoded form of x. e is the encoded form. जो बीच में आया था e वो encoded form था, और जो फाइनल हमारे पास आउटपुट जो x prime आई है दैट decoded form which is reconstructed form. ठीक है. So हमारा ट्रेनिंग हो जाएगी. once your network is trained, you will have all the parameters fixed, w1 and w2. are basically learned from training. ठीक है? So once they are fixed, you can then use the network. So given any new x, given any new x, you can get its x prime. ठीक है ना? आप उसका x prime आपके पास आ जाएगा. So now after this, you can now compute the Euclidean distance between x and x prime. And if this distance is greater than some threshold that you have specified, then you can say that x is an outlier. ठीक है? Okay, so that is essentially the idea. The idea is you reconstruct x given a model, and if that reconstruction varies significantly from the original x, then you can call it an outlier. So as I mentioned earlier, this technique is quite popular nowadays, although this technique is not given in a textbook. दोनों textbook में नहीं है, but it's commonly used in the industry. तो इसकी कुछ वजूहात हैं. एक तो of course this is unsupervised. It's an unsupervised approach, but इसमें जो न्यूरल नेटवर्क यूज हो रहा है, it is supervised, but उसमें supervision is kind of self supervision. मतलब आपको एक्सटर्नल लेबल्स नहीं चाहिए. आपका जो इनपुट एक्स था वही आप आउटपुट एक्स प्रिडिक्ट करना चाह रहे हैं, विच एक्चुअल आउटपुट जो आ रहा है एक्स प्राइम, यू लाइक इट टू बी एज क्लोज टू एक्स. तो इसको सेल्फ सुपरविजन कहते हैं. बट फ्रॉम आउटलायर डिटेक्शन परस्पेक्टिव, दिस इज एन अनसुपरवाइज्ड अप्रोच. हमारे पास कोई एक्सटर्नल इंफॉर्मेशन नहीं है. हमारे पास ये इंफॉर्मेशन नहीं है कि ये ऑब्जेक्ट इस आउटलायर है कि नहीं है. ठीक है? सो इट इज एन अनसुपरवाइज्ड अप्रोच फ्रॉम द पर्सपेक्टिव ऑफ आउटलायर डिटेक्शन. फ्रॉम द पर्सपेक्टिव ऑफ द ऑटो एनकोडर, इट इज एक्चुअली सेल्फ सुपरविजन. मतलब आपके पास जो भी इनपुट थी वही आउटपुट आपकी आप लेना चाह रहे हैं. ठीक है? So that's one thing. The other thing why this is popular, because it can be applied to all types of data. So can be applied to all attribute types. Okay, so your x could be an image, for example, as long as you can represent x as a vector or a matrix or in general a tensor, you can develop autoencoder on it. Okay, so x could be a vector, x could be an image, x could be a multi-dimensional tensor as well. So as long as you can represent your object in that form, it can be used. And let's say if you have numeric attributes, well and good, that works well. But let's say आपके पास categorical attributes भी हैं, तो उसको आप easily one hot encoding से या one of k encoding से इसको convert कर सकते हैं into numbers. So let's say आपके पास एक attribute है, let's say color है. So let's say you have three possible values R, G, and B. So obviously neural networks needs numbers to process, तो इसको आपको convert करना पड़ेगा. So what you can do is one hot representation इसको कहते हैं, से इसको convert कर सकते हैं. So since there are three possible values, you develop a vector of size 3, or there will be only one possible one there and all others will be 0. So if you want to represent red, you represent red as 1, 0 and 0. So पहली value 1 है. So if you want to represent green, then 0, 1 and 0. ये green represent हो जाएगा. If you want to represent blue, then 0, 0 and 1. This would be blue. ठीक है। ठीक है। सो तो आपके पास मिक्स्ड एट्रीब्यूट टाइप्स भी हैं, तो आप इसको नंबर्स में कन्वर्ट कर सकते हैं। लेट्स से आपके पास एज है, दिस इज नंबर ऑफ कोर्स, हाइट है, दिस इज नंबर, लेट्स से कस्टमर की इनकम है, एंड लेट्स से उसके कलर प्रेफरेंस है। ऑल ऑफ दिस कैन बी कन्वर्टेड इनटू नंबर्स। सो एज लेट्स से उसकी 25 है, uh, उसकी हाइट लेट्स से 175 है, एंड इनकम लेट्स से 50 है, 50K लेट्स से, एंड देन लेट्स से कलर्स को रेड प्रेफर होता है, तो यू हैव 1 0 एंड 0। ठीक है, तो इस तरह आप रिप्रेजेंट सब कुछ कर सकते हैं इस तरह। ऑर्डिनल वैल्यूज भी रिप्रेजेंट कर सकते हैं, नॉमिनल भी कर सकते हैं, न्यूमेरिक भी कर सकते हैं, एंड सो ऑन। दिस इज 1D, 2D में भी हो सकता है। लेट्स से इमेज है तो वो भी आप कर सकते हैं। ठीक है। So once you have this representation, you feed it into the autoencoder, you get the output, you train the autoencoder. Once the autoencoder has been trained, then given any new object, you feed it into the network, you get the encoding, you get the reconstructed value x prime, and compare it with the original x. If the difference is high and beyond a threshold that you have specified, then that would be an outlier. So by the way, ये जो था x minus x prime का norm, so you can use this as a score as well. So this is basically score. ठीक है, so this can be called a score, and then you can rank all objects according to the score. जिसका score एक threshold से ज़्यादा आ रहा है, तो you can call that those objects as outliers. ठीक है, so any questions on this? All right, so far we have looked at techniques that were unsupervised. So you can also have supervised approaches for outlier detection. So, so whenever we say supervised approaches, generally we will be falling into the domain of classification, because we are trying to distinguish whether an object is an outlier or not an outlier. Okay. So in supervised approach, so you need label data. Okay. So what do I mean by label data? You need to have some data that you have labeled already. So meaning that के आपके पास x है और class है हर object की, for some number of objects. ठीक है, I is equal to 1 to n. So this is our training data. You need to have a training data. So for example, x could be any object of interest. For example, customers को आपने देखना है कौन से customers are outlying customers. तो x would be representation of customers, और c जो होगा हर customer के against आपने बताया हुआ है कि ये outlier है कि नहीं है. So it's a binary classification problem. C would be binary, x is the input, So given such a data set, you can learn a binary classifier. So you can even learn a decision tree. So we had studied decision trees as a classifier in this course. So you can learn a decision tree that takes X as an input and would tell you whether that X is a outlying object or not. Okay. But as I said, you do need to have this data set. So once you have this data set, you train a model. Once the model has been trained, then that model can be used to predict for new objects whether they are outliers or not. Okay. So that is essentially the idea here. So you need to have a labeled data set and you can apply any classifier to build a model. Once the model has been built, you can use it for prediction. So this supervised approaches obviously suffer from the limitation that you need to have labeled data set. And for many applications, this is very difficult, sometimes even impossible. So as such, इसकी applicability कम हो जाती है supervised approaches की. Usually outlier detection के लिए हम unsupervised approaches ही use कर रहे होते हैं, unless we do have some data set which we can then use to fine tune the unsupervised approach, which leads us to semi-supervised techniques, which by the way we won't go into the detail. और कुछ थोड़ा बहुत लेबल डेटा भी है तो उस लेबल डेटा से आप अनसुपरवाइज्ड टेक्निक्स को भी आप ट्यून कर सकते हैं, तो वो बेसिकली सेमी सुपरवाइज्ड टेक्निक्स में आ जाता है. Alright, so any question? So in many of the algorithms that we saw for unsupervised outlier detection, you can think of those algorithms as giving you a score. ठीक है, जैसे LOF एक स्कोर देता है एंड ऑल्सो जो ऑटो एनकोडर जो है वो भी एक स्कोर देता है. तो यू कैन ऑलवेज रैंक द स्कोर एंड विजुलाइज द ऑब्जेक्ट्स टू डिसाइड द थ्रेशोल्ड. ठीक है. So this is generally a preferred approach rather than just someone telling you blindly कि ये outlier है, ये outlier नहीं है. तो if you have a score, आप scores को rank कर लें, जो highest scores हैं, maybe the top 10% of the score, उनको आप visualize कर लें. और visualize करने के बाद then you make an informed decision कि कहाँ आपने एक वो scores को cut off करना है, and those scores, those objects that are above this score would then be outliers. ठीक है, तो प्योरली ब्लाइंड अप्रोच नहीं होगी. बाय द वे जो क्लासिफिकेशन बेस्ड अप्रोचेज है उन मोस्ट क्लासिफिकेशन बेस्ड अप्रोचेज में भी स्कोर आता है, प्रोबेबिलिटी आएगी. तो प्रोबेबिलिटी दैट ए पर्टिकुलर ऑब्जेक्ट इज एन आउटलायर और नॉट, तो उस प्रोबेबिलिटी को भी आप रैंक करके फिर विजुलाइज कर सकते हैं. Okay, now briefly let's talk about two other types of outliers. By the way, most of the previous techniques that we saw were trying to find global or local outliers, local in the sense of LOF. Uh, so और ओरिजिनली हमने कहा था कि ग्लोबल आउटलायर्स होते हैं, कंटेक्चुअल आउटलायर्स होते हैं और कलेक्टिव आउटलायर्स होते हैं. तो लेट्स ब्रीफली लुक एट कंटेक्चुअल आउटलायर्स. वो क्या चीज़ है? So these outliers are defined by their context, and one way of defining the context is locality. वो हमने एक जगह पहले देख ली. LOF actually is a form of contextual outlier detection. But context could be beyond locality. It could be other things as well. ठीक है? So context could be time based as well. ठीक है? Context could be defined by other attributes. Uh, so for example, context ये भी हो सकता है कि profile of customer for example. ठीक है? So for example, customer आपका data set is about let's say customers of your company. तो उन customers को आप different profiles में कई दफ़ा divide कर लेते हैं. One customer is profile let's say one, या profiles को आपको नाम दे दें. Let's say this profile is of uh, let's say premium customer है, एक preferred customer है, एक normal customer है. तो इस तरह के let's say 3 profiles बनी हुई हैं. तो आप प्रोफाइल वाइज जब आप आउटलायर डिटेक्ट करेंगे तो दिस वुड देन बी कंटेक्सचुअल आउटलायर डिटेक्शन. ओके. so time wise for example, so you can think of let's say रिटेल इंडस्ट्री है, उसकी सेल्स का पैटर्न. लेट्स से योर कंपनी स्टार्टेड इन द लास्ट 5 years. तो पहले 2 साल में उनकी सेल्स बहुत थोड़ी थी, पर लास्ट 3 years में सेल्स बहुत ज़्यादा थी. तो ऑब्वियसली यू कैन नॉट consider the whole data set and try to find outliers. जो recent 3 साल की जो data है, that would be then be considered all outliers. तो उसका एक दूसरा तरीका ये कि consider the context. एक पिछले 3 साल का separate कर दें data और current जो latest 3 साल से separate कर लें, उसमें separately outliers निकालें. और जो first 2 years का उसको separate कर लें, उस पर separate outliers निकालें. ठीक है? So this is essentially what is meant by context contextual outliers. So you define a context and then you mine or you detect outliers within each context separately, not over the entire data set. So in general, you will have in any problem, you can sometimes divide your attributes into behavioral attributes and contextual. ठीक है? So in the case of let's say जो customer की मैंने बात की है, तो आपका जो contextual attribute would be let's say हमने देखना है कि प्रीमियम कस्टमर है या प्रीफर्ड कस्टमर, रेगुलर कस्टमर है. उसमें जो एट्रीब्यूट कंटेक्चुअल एट्रीब्यूट्स होंगे वो उसकी टोटल बाइंग वॉल्यूम क्या है, हाउ फ्रीक्वेंट दैट कस्टमर इज, एंड सो ऑन. सो ये चीज़ें वुड टेल अस वेदर ही बिलोंग्स टू ए प्रीफर्ड ग्रुप और टू ए प्रीमियम ग्रुप और ए रेगुलर ग्रुप. वाइल जो हम आउटलायर्स देखना चाहेंगे, जिन चीज़ों पे हम देखेंगे कि वो आउटलायर्स है कि नहीं है, वी माइट लुक एट जो बिहेवियर एट्रीब्यूट्स होंगे वो कि वो क्या चीज़ें खरीदता है. इज ही इंटरेस्टेड इन ग्रोसरीज और इलेक्ट्रॉनिक्स और सो ऑन. तो वो आपके बन जाएंगे दूसरे एट्रीब्यूट्स. और जो कंटेक्स्ट जो डिफाइन कर रहे हैं वो इस तरह की चीज़ें हो जाएंगी. कस्टमर्स लॉयल्टी टू योर कंपनी, द बाइंग वॉल्यूम टू योर कंपनी, बाइंग फ्रीक्वेंसी फ्रॉम योर कंपनी एंड सो ऑन. एंड उसके जो प्रोडक्ट्स वुड देन बिकम द अदर एट्रीब्यूट्स व्हिच यू देन ट्राई टू फाइंड उसमें से आउटलायर कौन सा है. So for example, just to again a hypothetical example, let's say आपने प्रीमियम कस्टमर्स का ग्रुप ढूंढ लिया. ठीक है? प्रीमियम कस्टमर्स हैं, these are customers that are loyal to your company, they buy a lot, they buy frequently and so on. अब इसके अंदर you detect outliers and you may find out that within this group most of the people buy let's say groceries for example. ठीक है? These people buy groceries from you regularly, maybe in high volume as well. बट इसमें से भी लेट्स से कुछ आउटलायर्स आपको मिल गए. एक आध आउटलायर कुछ तरह का, समवन हु बायज लेट्स से So some other product that you sell, let's say uh, crockery, for example. So someone who is buying crockery and he does belong to this group, so this would then be an outlier according to this setting. आपका behavioral attribute buying items की buying थी और आपका context was how loyal he was to your company, how frequent he bought, the total volume he bought. Okay, so these types of outliers would be contextual outliers. So in all of these cases that I've explained so far, context आपने खुद ही define किया, आपको पता था. Sometimes you don't know the context, तो उसके लिए it becomes a bit harder, but generally उसमें हम clustering करते हैं typically to first identify context. So of course, when you're doing this type of clustering, you will include the contextual attributes. Contextual attributes include करेंगे इस clustering में so that you can find groups that are separated using these contextual attributes. By the way, कई दफ़ा आपको contextual attributes पता भी नहीं होते, तो आप सारे attributes दे दें and then you do the clustering and then analyze the clusters. So once you have found those clusters and they seem to be relevant context for your analysis, then within each cluster, then you can apply any of those uh, outlier detection techniques that we talked about previously. ठीक है? All right. Uh, we also talked about another type of outlier which we called collective. So collective outliers is a group of objects which together form an outlier, while within that group a single object may not be an outlier. Okay, so that was the definition for collective outliers. और इसकी application जो हमने बताई थी, let's say the denial of service attack. Different computers are accessing a particular website. हर एक कंप्यूटर को separately देखें तो that person might look to be legitimately accessing a website. But जब multiple computers इकट्ठे एक time पे एक ही simultaneously एक साइट को access करने लगते हैं, तो then that becomes an outlier and we would like to detect that. ठीक है? तो इसमें भी actually this is very similar to contextual outliers. The only difference is the context is now defined more in a slightly sophisticated way, you can say, and it's also domain dependent. हर एक domain का context different होगा. तो denial of service attack का context different है, किसी और collective outliers का context would be different. तो ये at the end of the day, if you are able to identify the context, इसकी भी approach उसी तरह ही होगी जैसे contextual attributes की होगी. Find that group and then within the group try to find outliers. I think there इसके अलावा कोई खास इसके अंदर है नहीं. One other thing, I think I missed this last time. So we also said that among the approaches for finding outliers, we said we had statistical approaches, we had proximity-based approaches, we had clustering-based approaches, and we had reconstruction-based approaches. तो clustering-based approach में so essentially you're applying a clustering algorithm. तो इसमें I mentioned this last time as well, but let me just reiterate it here in a more structured way. तो इसमें तरीके क्या हो सकते हैं? एक तो हो सकता है कि आपका clustering algorithm identifies the outlier. An object is not clustered by the algo. then obviously this is an outlier, right? जैसे DB scan में there are some objects that are called outlier objects. They are not clustered, so that is an outlier by definition of the algorithm. ठीक है? So that is one way of identifying an outlier using clustering algorithm. So another way is an object is uh, uh, kind of quite dissimilar from a cluster, you can say centroid or medoid. तो आप Euclidean distance में देखेंगे तो object is far away from the cluster mean. And of course, far का कोई thresholding करेंगे. If that is far is beyond that threshold, then you will say that this is it's an outlier. Remember ये second case क्या है कि object हमारे algorithm ने cluster के अंदर ही दिया था. It's not outside a cluster. Let's say k-means में usually all objects would fall within clusters. उस केस में आपने फिर distance from of that object from the mean या some other representative point of that cluster लेके आपने decide करना है whether that's an outlier or not. ठीक है? And the third case may be कि your algorithm may find a cluster small, so an entire cluster that is small and quite dissimilar from other clusters. Okay? So now this is a group, usually a very small group of objects that have been found by your algorithm, but it's also quite far away from other clusters. So you can consider this whole group to be an outlier. By the way, this would be an example of a collective outlier. Actually, all of them would also be outliers individually. So collective जरूरी नहीं है, global outliers में ही आएगा ये, ठीक है? So this is the entire cluster that is now considered to be an outlier. सारे objects उसके अंदर outliers हैं. So I think that is essentially it for outlier detection. So we have considered a number of techniques, looked at uh, various ways of uh, detecting outliers. We also talked about different types of outliers. So, so one thing that you might take away from this is that outlier detection is not very rigid in the sense that or very automatic. It's not like if you push a button, you get an algorithm. You push a button, the algorithm will go ahead and find all the outliers for you. Human intervention यहाँ काफी ज़्यादा involve करनी पड़ेगी to get good results. It's not truly automatic. You have to be iterative and interactive. Or maybe you will have to apply different techniques. एक technique से शायद आपको reasonable results ना मिलें. And even after that, you'll have to do some visualization. Scores आपके पास आ गए, scores को देखें, and then decide whether an object is an outlier or not. So fully automatic इतना ज़्यादा नहीं है, except maybe for the very extreme cases. Okay. Okay. So any questions? Any questions?